In this video, we'll talk about similarity with area and volume. Now, when we talk about the similarity of shapes and solids and their scale factor, that is talking about one dimension, its length. When we want to move to the area of similar shapes, we're now going to have to look at two dimensions. So we have to take that scale factor and square it so that we can deal with both the length and the width being modified for the similarity. With volume, we will cube that scale factor because that scale factor must be applied to the length, the width, and the height. So those are key components when we're looking at similar solids as we move up into this progression. So let's say we want to determine the surface areas and volumes of two similar solids that have a scale factor of 3:2. That means that the ratio of the sides of the solids is 3:2. Now let's look at the surface area. With the surface area, I would be squaring this scale factor so that it changes both the length and the width. So 3:2 squared, I would distribute that square, so that's 3 squared to 2 squared, so the scale factor or the ratio of the areas would then become 9:4. When I'm looking at the volumes, I'm going to take the scale factor and cube it for the length, the width, and the height. So if I take that 3:2 cubed, I would do 3 cubed and 2 cubed so that the ratio of the volumes would be 27:8. And you can see how much dramatically bigger that is than where we originally started with the length scale factor. Now let's look at some examples here to help us out. Say we have these two rectangles and we want to determine the area of the large rectangle. Let's look at it two different ways. Now, one method would be to determine the corresponding side that's missing and then calculate the area of the large rectangle. So if I was to do this, I would recognize that I would have the 3 inches to the 6 inches equals the 5 inches to my unknown side up here. I can then cross multiply, and I would get 3 inches times x will equal 30 square inches. When I divide both sides by the 3 inches, that will simplify my units back down to the length of that side, which would be 10 inches. Now that I have both the length and the width of the rectangle, I can multiply them together to get their area, which would be 60 square inches. Now another method I could use is to create the proportion of the areas using the square of the scale factor, thinking about that big to small relationship. So if I look at this, this is 6 inches to 3 inches, which simplifies to 2:1. So each length is twice the length of the other side. When I'm talking about the areas then, I would square that. So 2:1 squared means that the area will be 4 times as large. So now I can set up and look at my areas. The first one, I recognize that the area of my small rectangle would be 15 square inches because it's a 3 by 5. And now I'm going to use the area of the large and the area of the small and that ratio of the areas to help me determine it. So 4:1 equals the area of the large to the area of the small. I cross multiply and I'll get the area of the large is 60 square inches again. So whether I calculate a missing side, which I can do in this case, or I use the ratio of the areas, I will still end up with the same area for this rectangle. Now sometimes you're not given all the information to allow you to do that. For example, here I have two rectangular prisms and I want to determine the volume of the smaller rectangular prism. I have the measurements of one and all I know is the scale factor. So yes, I could use the scale factor to find each of the length, the width, and the height of the rectangular prism, but let's focus on the idea of using the scale factor to help us look at the ratio of the volumes. So the ratio of the volumes is the scale factor cubed. So 3:1, if each of those are cubed, that will become 27:1. Now, I can use my volume of the large cube to help me find the volume of the small cube. So the volume of the large cube would be 3 feet by 15 feet by 9 feet, which is 405 cubic feet. So let's set up the proportion using the ratio and the information I do have about the volume of the large. So if I look at this as being large to small and large to small, I can then cross multiply, and then I can divide both sides by 27 to see the volume of the small cube would be 15 cubic feet. So the key is that relationship recognition that the scale factor cubed will give us the ratio of the volumes. Now, sometimes you're only given the surface areas or the volumes of similar solids. When this happens, say you have the surface areas. I'm going to calculate the scale factor by taking the square root of that relationship. The easiest way to do this is to write it as a ratio, the ratio as a fraction, so that you can complete the square root process. You can do that using something like Desmos or a TI calculator, and it'll help keep it in that fraction form for that ratio. Then we can use the scale factor to determine any of the missing lengths we may need or the volumes of the similar solids. We would use the same process if we're given volumes of similar solids, just to remember that the scale factor would have to take the cube root because of having the length, the width, and the height. So let's look at one last example. Say that we have the surface area of solid A is 30 square inches and the surface area of solid B is 750 square inches. If we know the volume of solid A is 200 cubic inches, let's determine the volume of solid B. So I don't have anything about the lengths or the widths or any of that information. All I have is the surface areas and the volume of solid A. So the first thing I want to do is take this from the surface area ratios back to the scale factor. So I need to take the square root of that ratio to create the scale factor. So if I think about this as being the surface area of A to the surface area of B, let's substitute in those values and take the square root. That would be 30 square inches to 750 square inches. And if I simplify that before I do the square root, I'd have 1/25. And the square root of 1/25 is 1/5. That's the scale factor. It's a 1:5 ratio of the lengths of solid A to solid B. Now, if you didn't go and simplify 330 over 750 and you just took the square root of that, the calculator will simplify it down for you. So you got opportunities about how you can go about doing these problems. Now that I have my scale factor, I can use that to create a proportion based on the ratio of the volumes. So if I think about what is that ratio of the volumes, I would have to do 1:5, and I would cube that. So 1 cubed is 1, 5 cubed is 1/25. So that's the ratio of the volumes. So the scale factor can then help me create the ratio of the volumes. And now that I have the ratio of the volumes, I can calculate the missing volume of solid B. So let's create a proportion. If I think about this as being the small solid A to solid B, the volume of solid A, 200 cubic inches, to the volume of solid B, now I can cross multiply and see that the volume of solid B would be 25,000 cubic inches.